Welcome, AP students. I trust that you had a nice break, a nice Easter break with your family. Maybe got a little rest, maybe did something that you would have enjoyed, maybe not just inside all of the entire time off. But anyways, today is Tuesday, April 14th, so 1 month exactly from today is your AP Chem exam. So it is going to be on May 14th at 2 p.m. I sent you a detailed email. I only got 3 students to respond back that they read it. I had asked that you respond, but nevertheless, that's why I wanted to just cover that quickly here. So it'll be at 2 p.m. through your computer, your AP classroom. So you'll have your calculator ready, some scrap paper, and it's 2 long free response questions. So covers anything within units 1 through 7. 8 and 9 will not be on there. I will not review 8 and 9. We did 8, but we did not completely finish 9. We had done part of 9. So anyways, I'm beginning today to go through Unit 4. So there will be 2 virtual lessons because I want to break it up so that it's not such a long video to watch. But please do try and watch these videos and also try the problems. Pause the video, work them out, see if you get the right answer. I'm going to try and talk about concepts and all that so that you have a refresher on Unit 4. Now you do have the Unit 4 PowerPoints already. You have the Unit 4 study guide. You have all the things you need in the notes you took previously. So those are all pertinent and useful. So I do suggest to review them. I have an AP Classroom quiz, Unit 4 review, coming up due here in the near future. So please check RenWeb for that particular due date. And it's also in AP Classroom for you. So let's get started on Unit 4 review, and it's on chemical reactions. So first off, a chemical reaction is a change in composition of some substance that was within the original makeup, within the reactant. Something changed. So remember, there is a difference. There's physical changes. They can be reversible or irreversible physical changes, like melting. That's a state change. That's reversible. But if you crushed, let's say you crushed an eggshell, well, you can't put that back together. It's irreversible. It's still a physical change. You still have the eggshell, but it's not in the same component as it was. Evaporation, all that is physical changes. Chemical changes has a different composition once it's done. Burning gasoline, hydrogen peroxide changing into hydrogen gas and water, burning a match, digesting food, frying an egg. It's different after it's gone through that process. So that is the difference between physical and chemical change. We'll talk a little bit more about that a little later in this particular lesson. So there are signs to tell that you had a chemical change, formation of a gas, bubbling, precipitate, that's a formation of a solid. That's where your solubility rules come into play, nag-sag. Color change is a sign of a chemical change. Production of heat or light. So you have an energy transfer. And then you have a change in mass. Either it's gain mass or loss mass. Now remember, conservation of mass means that both sides of the equation, reactants and products, are equal, but this is particularly talking about a substance involved in the reaction. You need to have a change in mass. That means you have some type of a change that has taken place, and it's a chemical change. So when you write a balanced chemical equation, you can write the full ionic equation or the net ionic equation. It's only involving what is actually taking place. So in this example here, we have a reaction of silver nitrate and potassium chromate, producing potassium nitrate and silver chromate, which happens to be a solid, so it's going to precipitate. So that is actually the only thing you're interested in if you talk about a net ionic equation. So that's why you have it here as your product side, because you're not really caring about the aqueous potassium nitrate. Those are spectators. So you have to break this up, and here is your 2 silver plus your chromate at 2- charge. You put them together and you have your solid precipitate. So let's practice this. So let's look at a couple examples here. So first off, we have sodium sulfide and silver nitrate are combined. I want the net ionic equation. So that's a great example of a question you very well could see on the AP exam. It does not tell you anything about the products. You're expected to know what will form from a reaction like this. So right away, I'm just going to write my formulas here. So I have sodium sulfide plus I have silver nitrate. So I have AgNO3 reacting to form, this is going to be sodium nitrate plus I have silver sulfide. And this here is a solid. So I have aqueous here, aqueous. Now I got to balance this because this is not balanced. I have 2 silver and only 1 silver on this side. So I need to put a 2 right here. I need to come over here and put a 2 there. So now I'm balanced. So this is my balance. I could break this up. It's not asking me to, so I'm not going to take the time to do that. But I am only interested in the net ionic equation. So I know I have to have what is producing that silver sulfide. So when I look on this other side here, I have my 2Ag plus, and that is aqueous, plus I have my sulfide here, 2-, and that is aqueous, and they are going to produce Ag2S, and that is solid. So here is my net ionic equation for this particular example. So remember, your net ionic equation is going to have gases, solids, liquids. Those are the things that you have to show in a net ionic equation. So here I have sulfur powder is burned in air. Write the net ionic equation. So sulfur powder, so I have sulfur solid. So it's burned in air, which is meaning oxygen. So I can write that down as O2, and that is a gas. And that's going to produce sulfur dioxide, and that is a gas. It's actually a toxic gas. So when you look at that, the actual balanced chemical equation is the net ionic equation on this particular example. So that's why I pulled this one out. That is your balanced chemical equation as well as your net ionic equation. You produce the gas and it shows the components that actually made that up. Let's look at another one here. So here I have fluorine gas is bubbled through a solution of sodium bromide. Write the net ionic equation. So fluorine gas, and I have, and that's a gas, plus I have through sodium bromide, so I have NaBr, and that is aqueous. And it's going to produce, well, it's going to produce sodium fluoride aqueous plus bromine, and bromine is a liquid. It's that reddish colored liquid. So, and that is Br2. Bromine is diatomic. So now I have to balance this. So I'm going to come over here and put a 2, and I'm going to come over here and put a 2. So that balances. I have F2, I have F2, 2Na, 2Na, and I got 2Br, 2Br. So now I want to write my net ionic equation. So I am only interested in the production of this, what is needed to produce that. So in order to produce that, I have to have my F2, and that is a gas, plus 2Br minus, and that is going to produce 2 fluorine minus. This was aqueous. This is aqueous. Plus Br2, and that is liquid. And this right here is my net ionic equation. It shows how, in fact, that is produced. And that's why you had to show the fluorine and the fluoride ions. You don't care about the sodium because it's a spectator, but this is directly involved in the production of that bromine. So that's why you have to show that. So hopefully you paused the video and you tried that. So now the next one here is a little tricky. This one here gets a little bit into some redox, and we're going to look at redox in the next virtual lesson. But just writing out what we have here, solid aluminum. So I'm going to go aluminum solid is dropped into tin sulfate. So I have SnSO4, and this is aqueous. And that's going to react to form tin, and this is solid, plus, and it's going to produce aqueous aluminum sulfate. All right, so let's balance this out here. So I got to come over here and put a 2. This is aqueous. I didn't write that. Let me put that down here. So I got to balance that. Got a 2 there. I have to come over here and put a 3, and then put a 3 on this side here. So now when I look at this, I want to write my net ionic equation. So the production of this tin right here. So I have to have 2 aluminum plus 3 2 plus 3 tin 2 plus reacts to form 3 tin solid plus 2 aluminum 3 plus. And this here is my net, and this is aqueous right here. This is aqueous, and this here was a solid. So this is my net ionic equation. So when I look at this, I have a 6 plus on the one side, and 2 and 3 plus is 6 plus. So I'm balanced, my charges are balanced, and my actual atoms are balanced. So that's really important. So that is a little bit tricky. So it is a little bit different. Hopefully you try that. You understand what I just explained on that. So this is my balanced chemical equation, and I've circled my net ionic equation for this example. Next, we have particulate diagrams. These are very common, very popular. You've looked at a lot of these. I have more assigned on the AP quiz coming up. But when I look at here, I have my methane, reacting with my two oxygens. Here's one and here's two. So I have one methane, two oxygens reacting, produce one carbon dioxide here. And then I have two water molecules. So this is looking at particulate diagrams, deciphering what it is. The center black is the carbon, and you can see that over here on this side. And the red is oxygen, so you have your carbon dioxide, and it gives you a nice visual representation of what is taking place in a reaction. So here is another example. Let's look at what this here says. So this is a particulate model, and it's just asking to explain what's happening from time 0 to 1 hour later. So let's determine what we have here. So red is oxygen, the black is carbon, and the white is hydrogen. So I have on this side carbon monoxide. Right here is carbon monoxide. I have water, H2O, which is right there. So when I look at this, I have 1, 2, 3, 4. So I have 4 carbon monoxide and I have 4 water molecules. 1 hour later, let's look at what I have here. So now I have right here is H2. So I have 3 H2s, hydrogen gas. I have some carbon dioxide, which I count here. I've got 3 of them, 3 CO2. I have 1 water right here. And I have 1 carbon monoxide. So that is what has transpired. So I went from 4 carbon monoxide and 4 water. 1 hour later, I have 3 hydrogen gas. I have 3 carbon dioxide. I have 1 water and 1 carbon monoxide molecule. So that is using a particulate diagram to talk about how things change in this particular reaction in a period of 1 hour. And it's not asking about anything, writing a equation or any of that. It's just asking to identify, and that's how you would use a particulate diagram to identify. When we talk about a chemical reaction, please remember there was that gray area. And when I say gray area, this is a physical change. I am adding salt to water, so I have this very strong bond. The water is going to split that ionic bond. It's going to take the Na plus and separate it from the Cl minus. And we already looked at this quite a number of times. And in this case here, we're going to have the oxygen surround with the partial negative charge. And on this side here, we're going to have the hydrogens surround it. And that's how exactly it is pulled apart by water. So there is some temperature change. So you could look at this as a gray area because it is not classified as a chemical change, even though there is some change in energy taking place. It takes energy to break this bond and to hold them apart like that. So there is some change, but it is still said to be a physical change. You can recover that sodium chloride by distilling it or allowing the water to evaporate. I just wanted to make sure we understood that concept. Now we're in stoichiometry, and remember, there are all kinds of stoichiometric calculations that we've done and we've looked at. We've looked at determining the limiting reagent. We talked about converting to moles and then dividing by the coefficients to determine from the reactant which one's limiting. The smallest mole would be the limiter. So we've looked at a lot of problems involving this. So I'm going to jump in, show us some example. Here's a pretty straightforward one here. I'm not going to work one like this. So it's asking you if you had 342 grams of the C8H18, and you want to know how much oxygen. Well, you convert it to moles, you do your mole conversion, and you convert that to grams, and then you get, in this case here, 1,200 grams. That's very straightforward. We've done those many times. But I want to look at some other types of examples. So let's look at this first one. You might want to look at it, pause the video, and work it, and see if you can get the correct response to these. What volume of a 0.35 molar NaCl solution is required to completely react with 39.0 milliliters of a 0.15 lead nitrate solution? So right away, hopefully you've already triggered that this is lead nitrate reacting with sodium chloride is going to produce lead chloride, which is insoluble. So it's going to precipitate. So that's why they want to know how much volume of the NaCl is needed to completely react with that. So the first thing you'll always want to do is just write your balanced chemical equation. So I'm going to set up here and I'm going to go NaCl, and this is aqueous, plus, and I have my lead nitrate, Pb, NO3, 2, and this is aqueous. And this is going to react to form sodium nitrate, and that is aqueous, plus, and then you're going to have your PbCl2, and that's a solid. So I got to balance this equation out here. So I need to come over here and put a 2. Come over here and put a 2. So I have 2Cl, 2Cl, 2Na, 2Na, 2 nitrate, 2 nitrate. So now I am balanced. So I'm going to start right away with my, right here, my lead nitrate. So I'm going to come over here and I'm going to write down 0.15 moles of PbNO3 over 1 liter. So I have right there 0.039 liters over 1. So that converts me, that cancels off my liters, now I'm in moles. So now I'm going to look at my stoichiometric calculations here. So I have to cancel out my lead nitrate to get to silver chloride. So I have 2 moles of sodium chloride to 1 mole of lead nitrate. So my lead nitrate cancel off right there. So now I'm in moles of NaCl, but I don't want to be in moles of NaCl. I have to cancel my moles. I know what that is right here. I have a 0.35 moles of NaCl in 1 liter of solution. And my moles of NaCl cancel off. So here I went from my moles canceling my liters because I have it was in molarity, did my molar conversion, went back to molarity. So I need to get my calculator here. So now I'm going to plug this in. So I'm going to go 0.15 times 0.039 times 2 divided by 0.35. So I should come up to, and I need how many sig figs? 2 sig figs. 0.033. 0.033 liters of 0.35 molar NaCl. So that is my answer. I could say 33 milliliters. Any of those would be correct. I could have converted that to 33 milliliters as well. But that's taking a stoichiometric problem with a little bit of a twist, because it's looking at molarity, converting from molarity to moles, and then back to molarity. And in this case here, finding my liters of solution. So hopefully you pause that. Hopefully you follow me on that. Let's look at another one. So here I have 42.5 milliliters of a solution of 0.25 molar potassium hydroxide. And it was required to completely titrate, and that's to get the equivalence, 47.1 milliliters of sulfuric acid. So find the concentration of sulfuric acid. So I have a strong base, strong acid. I could do this problem two different ways. I could do it the way I just did, or I could do it a different way. So why don't you pause the video, take a moment on that, and run through and see if you can do the calculations. All right, so let me talk on here a second. First off, always write down my balanced chemical equation. So I have my potassium hydroxide plus sulfuric acid reacting to form water plus potassium sulfate. So to balance this off, I need to put a 2 here, come back over to this side here and put a 2, and that balanced everything with that. So now I could use all my information right here. I could start with, I have 0.25 moles of KOH over 1 liter. I could multiply this by my liters here. So I have 0.0425 liters over 1. That liters cancel. That leaves me in moles. Do my mole conversion. So I have 1 mole of H2SO4 to 2 moles of KOH. And that cancels out my moles here. And then I could come back and go moles over liters, and it says I have 0.0471 liters. So this comes out to, if I plug this in my calculator, I have 0.25 times 0.0425 divided by 2. So I should come up to 0.11 molar H2SO4. But there's a simpler way to do this, and this is using the dilution formula. So I have my base and my acid. That's just, remember to write it like that. And I have M1V1 equals M2V2. All right, so when I look at this here, I have to remember, however, if I'm going to do this formula, I have to utilize it right, because look at my acid. It is not monoprotic, it is diprotic. So I'd have to put a 2 in the front here, and then I can use it. It'll work out just perfectly fine. So plugging this stuff in here, I'm going to have 0.25 molar. My volume is 42.5 milliliters equals 2 times, and we're just going to go M, and then times 47.1 milliliters. All right, so now if I take this and plug this into the calculator, 0.25 times 42.5. I should come out to the same thing, equals 0.11 molar H2SO4. So anytime you're dealing with a strong, you can use this dilution formula, save yourself some steps, some thought process, just plug it in. The main component you got to remember is it mono, di, or triprotic, because it could be either the acid or the base. So please keep that in mind. So here, in order to do this, you would have to have a 0.11 molar H2SO4 solution. All right, so tomorrow we will pick up on our next virtual lesson 3 types of reactions. Not talking about the single replacement, double replacement, synthesis, decomposition, combustion, not talking that. I'm talking about 3 basic reactions. You have precipitation reactions, acid-base reactions, and oxidation-reduction reactions, and that's the redox reactions. We know these as redox reactions, and we're going to look at each one of these. We've looked at this already today, and we looked at one of these in our activity here just a second ago. So we're going to cover more of these. We're going to practice several of them. I've assigned several of them in the AP classroom. So this is where I'm going to let off from this virtual lesson today. So we will pick up, and this was Unit 4 Review Part A. We will pick up on our next virtual lesson on Unit 4 Part B. So thank you for watching. Go in peace.